Welcome to the video lecture series of the course Computer Organization and Architecture. In last class, we have talked about how we can write control steps for given instruction. Means to execute any instruction, various control signals are issued by the control unit, and what should be the proper sequence of those control signals. Now, in this particular lecture, we will discuss what type of control organization we should design, so that we can write the control steps in a very efficient way. Means how control signals are generated by the control unit, that we are going to discuss. So, if any instruction is to be executed or any program is executed by the system, behind of that various type of micro operations are performed by the system, and for different micro operations different control signals are issued. So, programmers or researchers have devised few schemes, so that these control signals are to be handled by the system. So, there are two methods basically we study in this particular course. The number one method is hardwired control. So, in hardwired control, we can see in this figure there are several components. Means the device will issue the particular control signal based on some inputs. For example, we want to execute any instruction, add R1 R3. So, this we have done in last class already. So, what does it mean? It performs the operation R1 equals to R1 plus R3, where R3 register is having some address or address of second operand, and this operand has to be fetched from main memory. So, various control steps we have seen, various control signals are to be issued. The first step is instruction fetch, and to fetch the instruction, program counter will provide the address, and accordingly the memory address register will work, and the address is transferred through MAR, and the fetch operation will take place. The read signal will be issued accordingly, and after fetching, the instruction will be available with MDR register or memory data register, and which is transferred to instruction register, and from instruction register the instruction decoder will decode this instruction, and accordingly various control signals are issued. So, let us talk about in detail of this control, how this control unit will work and how these control signals are issued. Here we can see the generation of control signal will depend upon various inputs. So, here decoder and encoder is the combinational circuit, which takes few inputs from various units and accordingly generates output in terms of control signals. So, control step counter will basically contents of the control step counter is the proper or one of the input required for the decoder. So, it counts what step, how many steps are to be issued by the system to execute any given instruction. So, control step counter will count the number of steps, on it will keep record of different steps to execute this particular instruction. And these two inputs are also important, external inputs, some external interrupts or any other inputs are required, these are provided through these inputs, and some conditions are to be checked that are also handled by these condition codes. And based on these inputs, the encoder and decoder circuit will issue the control signals. So, in 7 step control signals we have seen various types of control commands are issued to execute this simple instruction or one instruction. So, let us see in detail. Here in this particular diagram, encoder and decoder are separated and their operations are different. In this particular case, we can understand. For example, these commands are to be issued by this unit, commands like AND or ZIN. So, we have seen in previous example where these commands were issued by the control unit. So, you can see the AND command was issued at clock number 7 and this was also issued in clock number or step number 5 when we were handling the branch operation, or also it was issued in case of conditional branch operation with these steps. In same way, the ZIN command or ZIN control was issued in first step and sixth step and fourth step of branch instruction or branch instruction execution step. So, here few more components are added. You can see step decoder provides separate signal lines for each step. So, this particular unit or step decoder will separate the lines for each signals, and the instruction decoder, this particular component instruction decoder gives separate line for each machine instruction, because to generate any to execute this instruction add R1 R3, several micro instructions or machine instructions are to be issued by the system. So, when particular machine instruction or control is issued, that will depend upon instruction decoder, which takes the input from instruction register, and several machine instructions are to be issued. Separate lines are given or produced by this instruction decoder based on given instruction. And finally, encoder will generate some output in terms of various commands based on these few inputs. So, step decoder will separate the line for each instruction and this instruction decoder will separate the line for each machine instruction, and based on these inputs the encoder will issue the control signal. This way hardwired control will work, or several controls are issued. So, let us see the internal architecture of this hardwired control. This is a combinational circuit of various AND and OR gates. Here you can see this is an array of OR gate and this is an array of AND gate. So, with the same example of 7 step, add R1 R3. So, let us recall this example once again. This instruction is fetched. So, first 3 steps are required to fetch the instruction from main memory where this instruction is stored, and this is the operand fetch step, means the second operand is given in memory location whose address is given in R3. So, you can see various commands are generated or various control signals are issued by this particular unit. When particular signal is to be issued, that depends on various inputs. So, let us take an example of ZIN for example. So, ZIN is issued, you can see in first step this, or in first step or in first clock cycle, that is why T1 is written here, and this ZIN is also issued in sixth with add command. You can see here in sixth step this ZIN is issued, and it is also available with unconditional branch at step number 4. When we are talking about unconditional branch, ZIN was issued or ZIN was used in fourth step. That is why T4.br is written. BR stands for unconditional branching. So, how the circuit can be generated, or you can see what should be the circuit to handle this type of to issue this type of control signal. What should be the circuit? So, you can see in this figure T1 is given here, it is OR with T4 dot branch and it is OR with add dot T6. So, this way we can understand. So, based on these inputs, these various inputs, particular one signal is issued. So, you can see it is a very complex architecture in hardware control. Let us take one more example of AND signal. In the same way, we can see the AND signal was issued in 7th step, this was issued in 5th step when we are talking about unconditional branch, and when we are talking about conditional branch, it was issued in different step. So, that was a conditional branch. When particular condition is met, then only branching is occurred. That means the PC value is updated with PC plus some offset value. When particular flag is less than 0 or negative flag is set, and if it is equal to 0, when this condition does not matched, then AND signal is issued. That means jumping to the previous location or starting location of instruction execution. So, this way we can handle or we can understand the architecture for AND signal. So, you can see, so T7, the 7th step was used for generating the signal AND, and the 5th step in case of unconditional branch, and in case of conditional branch T5 dot AND plus T4 dot AND complement, and so on. So, you can see it is a combination of AND and OR gate, and based on some condition these connections are given, or you can see based on these connections this AND signal will be generated. So, this way hardware control will issue different control signals to execute any given instruction. Let us see one more type of control, that is microprogram control. So, in case of microprogram control, the control signals are very similar to the, or the microprogram control is very similar to the machine language program. So, in the sense of, we can say, when we are writing some machine level language program, so that is very similar to the microprogram control, or microprogram control we can understand in the same way. So, let us talk about few abbreviations which are used in microprogram control. First is control word, or it is represented as CW. Control word is nothing but it is a individual bits represent the various control signals, and the microroutine, it is a sequence of control words or set of control words are given in some microroutine. Next is micro instruction. Individual control word in a microroutine is called as micro instruction, and the control store, it is a special type of memory where various type of microroutines or different micro instructions are stored. And microprogram counter, similar to program counter, there is a microprogram counter specially used for microprogram control. So, control signals are generated based on some condition or based on some instructions. So, how control signals are issued, or what should be the program, or what type of program has to be written, so that in a particular sequence particular control word is to be issued, or particular command is to be issued by the system, and how control signals are issued. In the same example, add R1 R3. There were 7 control steps we have seen, and different commands like PC out, Z in, end, MAR in, MDR out, and R1 out, R1 in, like different type of control signals we have seen in different steps. So, what should be the proper sequence of these signals and when these signals are to be issued? So, it depends on what architecture or what control handling we are using, either hardwired or microprogrammed. So, if we are using microprogram control, we have to write several control words or set of control words called as micro routine, or we have to write micro instruction to execute minute or micro operations which are used to perform micro operations. So, this way we can also handle issuing of various control signals. So, let us see the architecture of microprogram control. Here you can see instruction register, starting address generator, microprogram counter, clock, and it is control store. So, this particular starting address generator will issue the address of first micro instruction, where the first micro instruction or first control word is stored, and the clock driven microprogram counter will generate the address of generate a sequence of addresses of different micro instructions or control words. So, if we are using the same example, add R1 R3. So, there is a 7-step program, there is a 7-step control steps required, 5, 6 and 7, and in different steps various control signals are issued. So, we have to see in what step what type of control is to be generated, what should be the program for that. So, in this particular case, program counter will generate a sequence of these control words. The program counter is then automatically incremented by the clock. So, it is clock driven, automatically it is incremented by 1. So, that next micro instruction will be fetched, and the control store is a special type of memory where these control words are stored, or you can see you can understand this way, this is a memory where different micro routines are stored, and the output of this particular unit is in terms of control word. Based on these input, this particular unit or microprogram control will issue the control word, or you can say different bits are issued which are performing different operation. So, let us have one example of such type of architecture or microprogram control. The same example we are using here, add R1 R3. So, you can see the second operand is stored in memory location whose address is given in R3. So, this needs to be fetched from main memory, right, and the first operand is given in R1. So, to write this type of microprogram, we need to understand or we need to remember the same architecture, single bus organization where different components are connected. So, I am just quickly drawing this architecture. Here the PC program counter was given and 2 register related to MAR related to memory, that are MAR and MDR registers were there, and there was Y register which is the ALU register, and there was an ALU and few controls of arithmetic operations are given as input. There was some input of C in, carry in, it generates some output, and which that output or result will store in Z register, and here you can see instruction decoder which generates various types of control signals, and there was IR instruction register, and there are few general purpose register R0 to Rn -1, and there was some temp register. So, this was a simple architecture that we need to remember always. So, let us have a direction, proper direction. Now, you can see to execute this particular instruction, various components are utilized, and to control these components, different control signals are issued. So, when particular control signal is to be issued, that depends what type of program control we are using, either hardwired or microprogram control. So, if we are using microprogram control, in this case the 7-step program can be written like this. The program for to execute this instruction, this program has to be written. So, you can see there are several zeros and one combinations, sequence of zeros and ones are given. So, how these values are assigned to particular signals? Let us have there are thousands of controls that can be handled by this particular unit, or this organization can handle various type of controls. So, when particular control is to be issued and when particular control has to be generated by the system, that depends. So, in the same example you can see so here in first step the PC out, MAR in, read, clear Y, set carry in, add and Z in. These devices or these components are to be in function, are in function. So, they will have commands or control, they are instructed by the control unit. So, control signals for these components are to be issued. In first step you can see the PC out, MAR in, read, clear, Y, set carry in, add and Z in. So, these components are instructed through a control signals. Accordingly, they were assigned the bit 1. So, PC out is assigned as 1, MAR in is assigned as 1, read signal was there, that is why it is 1, and select and add and Z in, these signals are assigned as bit 1. So, we have to write first all type of operations this unit or this system can perform, means different type of components are there. So, all the components are to be written in this way. The first row is assigned various type of controls, means components which can perform in and out operation, reading and writing operation, and different signals which are required in different steps. So, these all combinations are given here. Now, accordingly, this instruction, if we are taking example of this instruction, so what are the control steps to required to execute this instruction? So, based on control steps, for example, in first step these components are working. So, we will assign 1 and remaining zeros. In second step you can see the PC in was enabled and Y in is enabled and Z out was enabled and WMFC signal was enabled. You can see in second step. So, Z out, PC in, Y in and WMFC, these signals or these components are working. Wait for memory function complete. In third step you can see the component MDR out or this signal has to be issued, the IR in signal has to be issued, because in third step we have fetched the instruction from memory and the instruction is available in MDR and this has to be transferred in instruction register. In fourth step you can see the MAR was enabled, read signal was given and R3 out, because second operand has to be fetched from main memory whose address is given in R3. So, R3 will provide an address and this address has to be transferred in MAR, and through MAR the memory will be indicated or marked and where the address has to be where the address of instruction is given, and the read signal is to be issued by the control unit to indicate the memory that fetch operation is going to be performed. And in fifth step you can see the Y in signal was enabled and R1 out signal is enabled and WMFC signal was given. Likewise, in sixth step and in seventh step various control signals are issued. So, who will control this particular sequence? The program counter, and how these instructions are or micro instructions are fetched. So, this is a micro routine, this is a micro routine and these are micro instructions for a particular step corresponding to different steps. So, this way microprogram control can handle the execution of instruction. So, let us have a detailed discussion of microprogram control. You can see here we can also handle, or this device can also, this control operation can also handle branch type of instructions, where we have to jump in particular location. So, in this particular case both the unconditional and conditional branch are handled. So, you can see here branch to starting address of appropriate micro routine. So, branch instruction will also be handled. So, starting and branch address generator will generate the initial or 0 location address or the first instruction address, and based on conditional and external inputs this will issue the this will generate the the address of instruction, where it has to be jumped. If it is unconditional branch, then it will directly jump to the particular location, and if it is conditional branch, then conditions are checked, and if these conditions are checked and met, okay, then it will jump onto the particular location and the operation of PC equals to PC plus of some offset value will be performed, and that location will be generated. And if this condition does not met, then it will go to the starting address or 0 location of the or the first address of the instruction or starting address of the instruction micro routine. So, that is all about this particular lecture, where we have seen different type of control units or program control. So, these are the operations we have seen, where how particular instruction is executed and how particular address of program counter through program counter is generated. So, this is the sequence of handling the branch type of instruction through the microprogram control. That is all. Thank you.